To Physics 2, Lab 4, Magnetic Braking with Faraday. This is the table of contents. So the goals of this lab were to collect observational data of a magnet falling through a conductive tube of aluminum foil and model the magnet falling through the aluminum foil tube computationally using OpenPython and compare the computational model with the observed data. So the key concepts that are used in this lab are Faraday's law, which says that the closed surface integral of the electric field over its outer edge is equal to the negative time derivative of magnetic flux. Lenz's law, which essentially says that nature abhors the change in flux and that it will create a force to try to counteract it. Magnetic flux, of course, is the concept of magnetic field going through a specific area, which, as you can see, this is the equation that defines it. So that force that Lenz's law was discussing is given here. Is equal. This is the equation to find it. It's I L cross B, and then we also will be applying Newton's third law and Ohm's law to calculate the currents and the forces. So here's a free body diagram of all of our forces. Our system is the falling magnet, and the aluminum foil and tube in the earth is the surroundings. We assume that the magnet has a north pole facing down, and that the only forces are the force of gravity. We ignore air resistance. So here's the procedure. Essentially, we just have the aluminum foil tube, and we have the magnet going through it, and so we drop it, and we repeat this procedure 5 times. So we have good trials, and we take the average of the data of the time that it takes for the magnet to fall through the aluminum tube. And so here are our results. The average time that we got was 0.724. So this is a computational model. This is just the first part of the code where I do the initial conditions. This is continuing with that. And so here's the part of the code where I visualize the velocity, and the vector is like the force, the magnetic field, the velocity, all that. Continue with that. This is the one where we calculate the magnitudes of all the forces and magnetic field and everything. And so these are the results of the computational model. What comes out to, so we use the magnetic dipole from our lab 3 and 1 model, and then and one running of the model, and then another running we used an observational magnetic dipole to calculate to do our calculations. So we saw from our results that the computational model, with both magnetic dipoles, it underestimated the time that it would take. It said about 3.1 seconds, and then it said 0.35 seconds and 3.31 seconds when the computational model was used, and then in real life it was around 7.35. This could be a result of the magnet hitting the side of the aluminum foil tube, which probably caused a lot of friction that would slow it down. That's likely the result of there's likely the cause of the error, but air resistance and timing errors also are potential sources of error. So what if there were holes in the tube? What would happen is there would be current flowing in those holes, or magnetic field flowing in those holes, so magnetic flux through those holes, and so there would also be eddy currents induced in those, which would cause perpendicular forces to move the magnet perpendicular to its velocity. It would also interrupt the normal area that the flux flows through, and so the current, the normal current that we talk about would be interrupted, and so it would fall faster because it would have less of a force to counteract the falling, and also it would be moving around sideways because there's perpendicular forces to do that. So if the resistivity of the conductor were reduced to close to 0, then it would not change the voltage difference, because the voltage difference is determined by the change in magnetic flux, which wouldn't be changing. However, the current and resistance relationship has to be constant, because that's the voltage difference. The voltage difference is constant. So as the resistance goes to 0, the current goes to infinity, and therefore the force goes to infinity because the force is scaled by the current. However, that's like a mathematical explanation, but what would really happen is once the force gets to a certain point where the magnet is not moving, the current will go to 0 because there's no more change in magnetic flux, and so it would completely stop, and gravity would take over again, but then the current would come back up, go back to infinity, and so it would keep the magnet in the same spot. It would just levitate. That's what would happen.